I'm kidding.
Welcome back, everybody. So this is the end of section 2.4, measures of variation. Whoa, excuse me. Thank you. So section 2.4, again, how is it different from 2.3? Well, 2.3 was about measures of central tendency, where you define the central to be a set of data. And section 2.4 is now, how do we define how spread apart a set of data is, right? We talked about range, very easy, very simple. We talked about deviation, where you've got to take your mean and calculate how far the piece of data deviates away from the mean. And then we talked about standard deviation, right? Standard deviation and variance, right? The formula for variance and standard deviation tie right together because variance is the square of the standard deviation, or in other words, standard deviation is the square root of variance. Remember, it's the sum of the x minus the mean squared divided by n, which is our total amount, and then we can square root that to find standard deviation. And then we got into, so we did population, and then we did sample. Remember, the difference being the oops, that's not n, the n minus 1. Right, that's the only difference with respect to the actual formula. I mean, I get it, we do x bar and we do at lowercase s and lowercase n. But again, and that should be evident from the context of the problem, whether you're using sample or population data, whether you're using parameters or statistics. All right. And then we talked about the empirical rule, right? The empirical rule. And because we said, so what does standard deviation mean, right? Standard deviation means it's just an amount that deviates away from the mean, right? An amount that deviates away from the mean. Standard deviation, which is always in the units of the original data, just tells you, well, if it's one standard deviation away from the mean, plus or minus, then a bulk of your data sits within that range. 68% if it's a bell-shaped curve. Now, this empirical rule is for if it's a bell-shaped curve, if it's normally distributed. Okay, that's how we say that. If it is normally distributed, then 68% of the data will fit within one standard deviation away from the mean. 2 standard deviations away from the mean, well, then we can encompass 95% of the data. We can definitively say that 95% of the data is within 2 standard deviations away from the mean. Within 3 standard deviations away from the mean, that's that 99 points, almost all of the data, right? Almost all of the data is within 3 standard deviations away from the mean. Is there outliers? Yeah, there can be. That could be 1 or 2 points. If there's a lot of points away, yeah, you could get 1 or 2 points out there, but most of the points fall within 1 to 2 standard deviations away from the mean. Only 5% should fall out of 2 standard deviations away from the mean. Then we did this one about the 67 and 76 inches. All right, so then we have this thing called Chebyshevs Theorem. Now, what's different from the empirical rule to Chebyshevs Theorem is that I am no longer assuming a bell-shaped curve. I am no longer assuming a normal distribution. You know, not every set of data is normally distributed. Maybe the data is abnormally, maybe skewed left, maybe skewed right. We don't know. You know, Chebyshevs is used when you either don't know or you know it at least not normally distributed, right? The portion of any data set lying within k standard deviations, so lying within 1 or 2 or 3 standard deviations, can be approximated 1 minus 1 over k squared. 1 minus 1 over k squared. So we can say, as long as k is greater than 1, right? If k is 1, then it's 1 minus 1, and that's 0. So for any k greater than 1. So if we want 2 standard deviations away from the mean, I can just take 1 minus 1 over 2 squared. 1 minus 1 over 2 squared, right? 1 minus 1 over 2 squared, that would be like 1 minus 1 over 4, so 0.75. 1 minus a quarter is 0.75. So we can say that even if the data is not normally distributed, we know at least 75% of the data will fall between two standard deviations above and below the mean. For k equals 3, we can say 1 minus 1 over 3 squared. So 1 minus 1/9, or 8/9, or 0.8 repeating, which is 8/9, right? So 88.9% of the data will fit within 3 standard deviations away from the mean. Even if the data is not normally distributed, or even if we don't know the data is normally distributed, we can say definitively that 88.9% of the data will lie within 3 standard deviations away from the mean. And again, how do you know whether it's normally distributed or not? It's the context. Read the problem. Are you specifically told that the data fits to a bell-shaped curve? Are you specifically told that it is normally distributed? If it's not, if you don't have that wording in there, then you have to use this. 1 minus 1 over k squared, where k is the number of standard deviations away from the mean. And that could keep going. You know, if you have four standard deviations away from the mean, that would be algebra 1. Yeah. Hold on a second. Pause. This ostrich needs something. Pause. Time out. I need to pause the video. Pause the video. And we're back. Come on. There we go. You know, and this process could continue. You know, if I wanted to say within 4 standard deviations away from the mean. Now, if it was the empirical rule and I said 4 standard deviations away from the mean, that's like rounded, you know, rounded wise, it would probably be like 100% is within 4 standard deviations away from the mean. But if I said using Chebyshevs rule, well, that would be 1 minus 1 over 4 squared, right? So that would be 15/16. So if I didn't know it was normally distributed, I could definitively say that 93.75% of the data would fit between 4 standard deviations away above or below. All right, so how does that help us here? Suppose the mean baseball player salary is $5 million and that the standard deviation is 1 million. Using Chebyshevs theorem, what can you conclude when k equals 2? And how about when k equals 3? Am I told that baseball players' salaries are normally distributed? No. And that's why I have to use Chebyshevs theorem. Okay? And it's kind of fun to say.
Could you always use Chebyshevs?
Yes, because it is a lower estimate.
Okay.
Right? But if I say that it is normally distributed, you'll be expected to use the empirical rule because it's a more exact estimate.
What word again?
The empirical rule. Oh, normally distributed.
No.
Or bell-shaped curve.
What's the other one?
What's the other one?
It's kind of. I think it starts with a C.
Empirical rule? Or this guy, Chebyshev?
Yeah.
Yeah, you just wanted me to say it again.
Yeah.
All right, suppose the mean baseball player salary is $5 million and that the standard deviation is 1 million. Using Chebyshevs theorem, what can you conclude upon k equals 2? Okay, so when k equals 2, then you know that 1 minus 1 over 2 squared, well, that's 1 minus 1/4, or 3/4, or 75%. Right? 75%. So what can we conclude? We can say that 75% of baseball players make what? Make what? Not more than 6. Oh, 4 to 6, you're close. K is 2. 3 to 7. 3 to 7. Make 3 to 7 million. Does that make sense? Because they make within 2 standard deviations away from the mean. If the standard deviation is 1 million and my mean is 5 million, then I can go as low as 3 and as high as 7 and definitively say that at least, and I can use that terminology, at least 75% of the data fits within 2 standard deviations. So at least 75% of baseball players make $3 to $7 million. Now, if this was normally distributed, that would still be true. But now I could increase that value to say 95% of baseball players make within $3 to $7 million. Does that make sense? So Chebyshevs theorem is a lower, it's like less confident. You know what I mean? If you're using normally distributed or bell-shaped curve, then you can say a little bit more percent falls within there. So if k is equal to 3, well, that would turn into 1 minus, 1 minus 1 over 3 squared, so 1 minus 1/9, or 8/9, which is 88.9%. So we can say that 88.9% of baseball players make how much? 2 to 8. You can add and subtract 1. Good job.
1 million.
1 million. Yeah. Questions about that? Nope. Good. All right. So let's talk about standard deviation for grouped data. Standard deviation for grouped data. Like for example, I take a frequency distribution of grades in the class, and I want to know how much my standard deviation is, but I don't know all the sample, right? All I am told is the frequency distribution. How do you tell a standard deviation based on the frequency distribution? For a frequency distribution, the sample standard deviation, and again, if it's a frequency distribution, obviously you take it, well, I guess population or sample. But here's a sample standard deviation for frequency distribution. You take sum of the x minus x bar squared times f. F is the frequency, right? Sum of the deviations squared times your frequency divided by n minus 1. Where n is the sum of all the frequencies added together. My freshmen spilled their water bottle.
Of course, the freshman did
Hey,
Those are got all over the wall and all over
that. Was it intentional?
I'm gonna be a freshman next year.
Yo.
Yeah, that's true.
That's
we're degrading.
True. Yeah, you're gonna regress a little bit.
Evolving. I'll put the food chain to the bottom. Bro.
You never stay on top.
All right, so let's take a look. Let's do an example of this. Now, this takes a little bit of work. Yeah, this takes a little bit of work. And again, it's not mathematically difficult. It is consistent. You know, you just got to be consistent. You got to be careful. Okay, to calculate standard deviation. I didn't even tell you to calculate standard deviation. Let's say we wanted to calculate standard deviation. And I guess I should use S because it's the same. A group of students was asked how many TVs were in their house. So S is going to be equal to the square root of the sum of x minus x bar squared times f, all divided by n minus 1. Now, to calculate x minus x bar squared, do I have x bar?
You gotta find it.
We got to find it. We don't, but we can find it, right? So then that reverts back to, okay, so what's the formula for x bar within a frequency, right? Well, that is xf, sum of xf divided by n, right? Yeah. Sum of xf divided by n. Sum of xf divided by n. So let's do that first.
1.8.
No way. You already did that?
And it said,
Dang, man. What'd you do? Did you just add up f?
Yeah. Divided by 5, right?
No.
Oh, really?
No. You got to take xf because you're not taking it. You're just adding the frequencies divided by 5. The average frequency is that. But you got to find the average x value with that frequency. So you got to do xf's. So this is xf. And then we take, okay, so 0, 8, 50, 60, 12, and 5. Does that make sense? Yeah. So now let's add that together. 8, 50, 60, so it was 110. And then 12 and 5 make 17. So 135. So that's sum of xf, right? And what is n? N is what here?
Well, 5 minus 1, 4.
Now, be careful. Is it sum of the x or sum of the f's? Sum of the f's. Got to add up all those together.
Where do you see that?
What's that? You just got to know that.
Okay.
So the n value, like think about the n value is how many people I'm serving, right? So if 2 people said 0, 8 people said 1, 25 people said 2, 20 people said 3, 3 people said 4, 1 person said 5. How many people did I survey? That's the sum of the frequencies.
Gotcha.
Does that make sense?
Yes.
Okay, so this is 10 plus 45, so 55 plus 4, 59. Oh yeah, 59. Yeah. So the sum there is 59. So that means my average, my x bar, is 135 over 59, which is 2.3 for our rounding purposes. Yep, that's what I got, 2.3. So that means within our frequency distribution, the average person of what we surveyed has about 2.3 TVs in their house. Take a third of a TV. All right, so now to find the standard deviation. So how far spread apart is our data, right? That's what we're looking at now. To find our standard deviation, I've got to find the sum of the x minus x bar squared times f, right? Sum of x minus x bar squared times f. So I'm going to take sum of x minus x bar squared and then multiply it by f for each one of these. So I'm just going to add on. Got to stay organized. Organization is key. It can go up again. Sum of x minus x bar squared times f. So I'm going to take x, 0, minus 2 point, what did we say, 2.3? 2.3 minus 2.3 squared times my frequency, which is 2 in this case. Everybody follow me there for that calculation?
Yeah.
10.58. And again, this is x minus x bar squared times my frequency. So let's run the rest of the values. So now I have, we have 1 minus 2.3, and my frequency was 8 people said 1. So 13.52. And for the response of 2, I got 25 people said 2. 2.25. Now, why did that number go down? So many more people said that. Why did that number go down so much?
It's closer to the mean.
Because it's closer to the mean, right? Standard deviation, you're going to get lower numbers the closer you get toward the mean. So now I do the same thing, but with a 3 response, and 20 people said 3. 9.8.
Wait, but then why is the first one a smaller number than the second?
Because only 2 people said it. It was further away from the mean, but only 2 people said it.
Okay.
And then 4, oops, come on, buddy. 4, how many people said 4? Only 3. 8.67. Yeah, and even though 3 was closer to the mean, it was because so many more people said 3.
Yeah, that's good.
And then we have 5, and 1 person said 5. 7.29. Okay, so I add all this together, and this is going to be my numerator underneath my square root. So I've got 10.58, 13.52, 2.25, 9.8, 8.67, and 7.29. Just double check. 10.58, 13.52, 2.25, 9.8. 52.11. Okay, so standard deviation is the square root of 52.11 divided by what? 58 and minus 1. Okay. 52.11 divided by 58. Square root. 0.95. That's my standard deviation. And what can we say based on that? Well, we know 2 standard deviations above and below the mean. So what's my mean? 2.3. So to 4.3 to 0.3. Now, do I assume that this is bell-shaped?
No.
No. I can say 75% of the data fits within 2 standard deviations away from the mean. That's Chebyshevs theorem, not the empirical rule, because we don't know bell shape. 75% of people responded within 2 standard deviations away from the mean. So that means within 0.3 to 4 point something, right? And actually, we know more than that, dude, because we only have 1 person. Well, 3 people outside of that range. Can't believe 2 people don't even have TVs. Impossible. Well, I guess people watch stuff on their phones and stuff.
Netflix.
Ew.
No, you still got a TV.
You still got a TV.
Yeah.
Still got a TV.
That ain't right.
Still got a TV. All right. Last thing that we'll talk about: standard deviation when the frequency table has when the frequency table has classes. Okay, when the frequency table has classes. When this is the case, you estimate the sample mean and standard deviation by using the midpoint of each class. Yeah. So you know how we had an X as our response, right? That was I either have 0, 1, 2, 3, 4, or 5 TVs, and that was it. There was no range of values that I could have responded in. Okay, if I had said, well, I'm going to calculate the average high temperatures in the month of January, and I was going to group them, and I said, okay, I'm going to find the days that had an average high temperature from 20 to 25, and then from 26 to 30, and so forth, right? Because I have a range of data that falls in there, I have to use the midpoint of each class as my X value. So for example, assume the following grade distribution. So I have from 61 to 70, I've got 4 people. From 71 to 80, I've got 5 people. 81 to 90, I've got 9 people. 91 to 100 is 2 people. Now, if this is the case, I again have to I basically have to do the exact same thing as I did on the last one, right? I have to figure out my X bar. And remember, X bar is the sum of your XFs divided by N. And then I'll have to figure out my standard deviation, right? Standard deviation is the square root of sum of the X minus X bar squared Fs divided by N minus 1. Now, for those of you wondering, you will have all of these formulas on your test, right? And this foldout that you have in your book has all of these formulas on them. You will get that exact same thing on every test. Deal?
Deal.
Make sense?
Yes.
So, do you have to memorize that formula?
No.
Nope. Does it have Chebyshevs theorem on it too?
Hopefully.
I wouldn't see why not. Yep, it does. Okay. Now, it does not tell you what everything means. You know, like it doesn't define what X is. It doesn't define what F is. It doesn't define what N is. So you have to, it just has the formulas there. I mean, they're pretty self-explanatory. Anyway, just saying. All right. The first thing that I need to do is calculate the midpoint, right? Let's calculate the midpoints. Okay, so the midpoint of 61 to 70. Oops, 61 plus 70 divided by 2 is 65.5. Okay, so now I can use those as my new X, right? So 75.5, 85.5, 95.5. So to find our mean, I'm going to find the XFs. Okay, 64 times 65.5. Oops. Gets us 262. 5 times 75.5 gets us 377.5. 9, we're in the 85 range. 769.5. And then 2 people got in the 95.5 range. So 191. Okay, so let's add all of that together. 262, not times, plus 377.5, plus 769.5, plus 191. 262, 377.5, 771, 1,600. Okay, so that's sum of xf's divided by n. And now what is n? What am I going to add up to find n? F. Yeah, this is going to be n, right? So how many people did I have in the class? Looks like 20. So I take, now this is just divided by n, not n minus 1. So 1,600 divided by 20 gives me 80%. Average score was an 80. Okay, so now I take x minus x bar squared times f. X minus x bar squared. And when I say x here, I'm dealing with my midpoints, right? So I've got 65.5 minus 80 squared times the frequency of 4 in this case, 841. And again, this is x minus x bar squared times my frequency. Okay, let's do that calculation again, but now instead of 65.5, 75.5, and the frequency was 5 instead of 4. 101.25. And now we do the same thing, but now for 85.5, and my frequency was 9. 272.25. And our last one, for 95 range and 2 people, 480.5. Okay, let's add all those up together. 841, 101.25, 272.25, and 480.5. 841, 101.25, 272.25, 480.5 gets us 1695. Okay, so my standard deviation is 1695 divided by what? 19. Yeah, you took the x bar. 19, and then when I square root it. So I take this, divide by 19, and square root that number. 9.4. S is 9.4. And then I can tell all of those things about my frequency distribution now. Now I know that, okay, the 75% of my people, actually, you know, it's interesting here. My average was an 80, right? Yeah. What's 2 standard deviations above and below? 99, 61, right? So I say at least 75% of my Chebyshevs theorem says at least 75% of my data falls between 61 and 99. What do we know logically? Well, I guess I don't know. Maybe these 2 got 100, right? But we could say probably a lot more than that, right? Probably a lot more than that. Almost all of it lies between 2 standard deviations. You know, and we went even far as to say, what was 3 standard deviations away? 88.9%, right? definitively 100% of my data fits within 3 standard deviations away. Right? So maybe my grades are more bell-shaped. All right, let me stop the video there. That's it for this lesson.